Hello, and welcome to today's webinar, Galileo High Accuracy Service Features, Hardware, and Applications, brought to you by GPS World Magazine and our sponsor of the event, Talisman. I'm Jessie Khalil from North Coast Media, the digital media editor for GPS World, and I will be your event manager for today's presentation. At this time, I'd like to get you comfortable with your console and the way you can participate during today's presentation. Please notice the Q&A panel on the left-hand side of your console. If you have a question, type it in the panel text box, then click Submit to place your question in the queue. You may also use the hashtag GPSWorldWebinar on Twitter to submit questions during today's webinar, or to enter into discussions with other attendees. We encourage you to ask and enter any questions you may have for our speakers during the presentation. We will address these questions at the end of the presentation during the Q&A portion. Questions submitted during the registration have already gone to our speakers and may be covered during the presentation. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issues, and our technical support specialist, Brian Davis, or I will personally assist you. Finally, you may learn more about today's speakers by viewing their photos, bio, and contact information in the panel located in the upper right-hand corner of your console. Now, I'd like to introduce today's speakers. Today, we will be hearing from Sunil Bisnath, a professor of geometrics engineering, Department of Earth and Science and Space Science and Engineering, Lasdone School of Engineering at York University. We will also hear from Joseph Botros, the Senior RF and Antenna Designer at Talisman. And lastly, Jean-Yves Latour, Chief Technology Officer at EOS Positioning Systems. At this time, I'll turn the presentation over to Sunil. Take it away.
Thanks, Jessie. Hi, everyone. So the first part of this webinar, we'll talk about precise point positioning, or PPP, and the Galileo High Accuracy Service. So as most of you know, Galileo is a European Union service. The initial service began in 2016, and currently there are 23 usable satellites in the constellation. Galileo provides a number of different service levels. The first is the open service level, or OS, and this is the open free service that provides positioning and timing information, as well as the navigation message to produce what most people use as Galileo. There's also the public regulated service, PRS, that's restricted for government authorized users. The search and rescue, or the SAR service, that's a satellite-based search and rescue alert detection system. And finally, there's the High Accuracy Service, or HAS, the subject of today's webinar. This complements the open service, that is, it's added to it by providing additional navigation signals and value-added services at a different frequency band, and it can be encrypted to control access. In order to talk about HAS, we might talk about the OS for a second, and more generally, what is considered the standard positioning versus precise positioning. So in this figure on the top graphic, we have what we call standard positioning for any GNSS. The first component is that we have meter level real-time broadcast of orbit and clock information. That's coupled with receiver tracking information, usually in the form of the pseudo range or code measurements on one frequency. And this is this information is combined in an estimation process, an epoch by epoch or epoch-wise estimation process. And the result is meter level user position and equivalently timing information. For precise positioning, this is expanded. We either replace or we augment the broadcast orbits and clocks that are at the meter level with centimeter level versions. We use the tracking information in the receiver on multiple frequencies, and we also incorporate the carrier phase measurements. We do additional error modeling and then do filtering of all these code and phase measurements to produce anywhere from decimeter all the way down to centimeter level positions. So we can see the similarities and differences between point positioning and precise point positioning. PBP is a measurement-driven technique, and what we see in this figure on the x-axis is increasing precision or accuracy from decimeter down to millimeter level, and on the y-axis, the reduction of the initial convergence time, because the technique relies on the pseudo-range measurements to begin the positioning process. It starts off at a meter level solution and then converges either slowly or quickly, depending on what we do in the PBP processing. So what we see in that XY plot is a progression of adding information. And then we see increased precision and accuracy of the solution and reduction in the initial convergence time from float GPS to fixed GPS, fixed GNSS, and then multi-frequency, multi-constellation fixed GNSS. And what we mean by fixing is that we're fixing the carrier phase ambiguities in the process. This whole situation is also a function of additional information. So if we are able to provide ionospheric information about ionospheric refraction, tropo information for tropospheric refraction, these will improve the quality and the speed at which we can obtain this positioning. Also, the quality of the hardware used and the quality of all the corrections in the process, as well as the software that's used and the static and kinematic, and of course, the open sky environment, all play a role in the quality of the overall positioning that can be done. So where does that lead us to? Well, there are many services that are out there that are offline services, real-time commercial services, et cetera, that have proliferated over the years. But what we're talking about here is navigation satellite system-based PPP corrections. So coming from the constellations themselves. So what the constellations are doing in the purple, for example, the OS, is to get meter level PNT, positioning, navigation, timing. That's a function of the satellite orbits and clocks, plus trilateration, which is the ranging of the timing signals being received from multiple satellites to the receiver. In order to produce decimeter or better level PNT via the use of PPP, we do the above, plus we need additional corrections to the satellite orbits, clocks, and other information, which we'll talk about in a minute, to enhance that solution, to augment that solution. These corrections can either be transmitted by the constellation and then take advantage of the MEO nature of the constellation to receive the corrections, or via the internet, if that's another option with certain services. And the corrections are in what's called state-space representation, or SSR representation. So rather than correcting the ranges, these are corrections to states in the estimation process. Now, there are other systems with such capabilities other than Galileo HAS. There's QZSS and Beto with certain geographic restrictions. In all cases, the last bullet's important, is that the user is responsible for producing the P&T solutions via the PPP process that we just talked about. So coming back to HAS, what exactly is being provided? Well, there are two service levels, Service Level 1 and Service Level 2, that the constellation's working towards. For Service Level 1, the coverage will be global, and the types of corrections for PPP are the satellite orbits, clocks, and biases, both code and phase biases, which will allow us to do carrier phase ambiguity resolution. The format is very similar to the compact SSR or CSSR format. the corrections will be provided for Galileo satellites and GPS satellites. So as long as you receive the standard broadcast messages from those two constellations, you can then correct them and we have a listing of the particular frequencies on the two constellations that corrections are applied to. Of interest to most people are the accuracies. So the expected horizontal accuracy at the 95% level would be less than 20 centimeters, vertically 40 centimeters, convergence time less than 300 seconds, and available 99% of the time with a 24/7 help desk. For service level 2, the differences are that the coverage is for Europe, and the corrections are the same, but the additional ones are atmospheric corrections, ionospheric, and perhaps tropospheric corrections. And the result will be for over Europe, not necessarily an increase in accuracy, but a reduction in that initial convergence time to less than 100 seconds. What are the target markets for HAS? There's quite a list here. I won't go through all of them, but just to verbally say, geomatics applications for mapping, agricultural, aviation, road, consumer solutions, location-based services being a very large part of that, rail, maritime, and space. So it covers quite a wide swath of markets. The Galileo interface control document was provided in May of last year. And this document is freely available at this website and it provides exactly how to make use of the HAS signal. So there's service level 1 and service level 2, but HAS has phases in terms of its rollout. Phase 0 was a testing and experiment phase. We've gone through that. We're now into phase 1, the initial service. And then later on, we'll come to phase 2. So what we're seeing right now with phase 1 is Galileo and GPS orbit and clock corrections along with code biases, but not phase biases. So we cannot produce fixed solutions, just float solutions at this time for the frequencies that are listed here. So to give a sense of some of the early analysis, so we were able to look at some of the correction data last year. So this is late last year, and what we can see on this plot are E are the Galileo satellites, G are the GPS satellites, and the correction availability percentage. Those numbers were 97 and 91% for Galileo and GPS respectively in late 2022. We redid this analysis earlier this year, and Galileo is up to 99%, GPS at 92%, so approaching the SL1 requirements. If we look at the corrections themselves, the orbit and the clock corrections, and we compare them against high quality post-processed products from other centers, we can see the quality of those orbit and clock corrections. GPS on the figure on the left, GPS in the blue, and Galileo in the orange. And while we do see some outliers in the clock, we have the statistics here on the right for the 3D clock quality and the 3D orbit quality and the 3D clock quality, about 9 centimeters and 15 centimeters respectively. Another area of analysis that's of interest is what's called the signal in space range error. So the quality of the range that we're receiving, and we have the orbit on the top figure and the total, which is the orbit plus the clock components in this figure, and we do see good stable performance given that there are a few outliers, and that remains. So the last part of this segment, we're looking at some of the positioning performance with our own PVP engine. So what we did is we took a set of high performance stations from the International GNSS service, the IGS, spread around the world from late 2022. And you see this in the distribution here, so trying to cover the entire planet. And we performed some analysis. And so the first we have here is for these static stations, these cores, convergence performance up to the 20 centimeter horizontal and 40 centimeter vertical targets from the service level 1 and 2. And what we can see in the figure, if your eyes look at the yellow, this is for the static PPP processing, and we can see the Galileo only, the GPS only, and then the combined Galileo and GPS results, and how many minutes it took to get to that quality of result at the 95% and 67% level. And of most interest, for example, is the horizontal 95% and about six minutes. Keeping in mind, we don't have the phase biases, but with them, the convergence will happen more quickly. So some current performance. In terms of overall accuracy, if we process 3 hours of data, this slide shows some of that. And again, horizontal performance for static and kinematic processing of the stationary data, where a little over 10 centimeters, 95% for the horizontal RMS. One issue that's been raised recently has to do with the ground station network that's currently being used in phase 1. Ideally, the system would want to have more ground stations. And so we do see that at some stations, the convergence performance is not as good as in others. And so what we have in this figure are the stations in Europe in yellow. And then as we move east-west away from Europe, so as a function of longitude, we see that there is some correlation in the darker colored lines being from different continents. So we get to some stations in North America and South America, and we see that the convergence time does end up increasing. And finally, the audience may be of interest in kinematic data. So in this case, we have suburban data collected in a vehicle in the city of Toronto, Canada. This is a talisman antenna and a mosaic receiver in a real world environment with trees and vehicles, etc. And we have in the red the point positioning solution using GPS and Galileo, and then the HAS solution. And this was collected relatively recently. And what we see in the results is that the HAS solution is much smoother. They're both collected in real time, and so it's real time processing. But with the HAS PPP solution, even without the phase biases, is much smoother. However, one thing we do see is there is some availability issues where you have fewer satellites with the HAS corrections. But we can see an overall improvement in the RMS from 1.2 meters down to 0.6, so a 50% improvement. With that, I'd like to pass the webinar on to the next segment with Joe.
Thanks, Sunil. Hello, everyone. Now we move on to the next part of the webinar, talking about antenna considerations for using Galileo's High Accuracy Service, or HAS. Let's go through an overview before we begin. First, I'll go through the evolution of GNSS. Next, I'll talk about what makes a good antenna. Following that, I'll go through existing solutions which cover Galileo's High Accuracy Service, followed by a few notes on novel solutions which do the same. Finally, I'll go through a quick recap. Starting off with the evolution of GNSS. At first, there was nothing. Seafarers and travelers knew their way only by using maps, compasses, sextants, and the ever-present stars. All that changed with the introduction of GPS. And then GLONASS, and the European Space Agency's Galileo, and then Beidou, in addition to other regional global navigation systems. With all these constellations, we need multi-constellation antennas. E6 is the new frequency band that carries Galileo's High Accuracy Service, or HAS signal. That means traditional dual or triple band antennas now need at least a 50% increase in bandwidth to cover this new and valuable correction service. With the advent of GPS, most commercially available antennas were designed to cover only L1. Dual band solutions emerged to take advantage of GPS L1 and L2 signals, providing more precision by correcting for atmospheric effects. These first designs were generally for professional applications like military, surveying, and for geodetic solutions. Therefore, there was little concern for swap-C, which is size, weight, power consumption, and cost. Today, as we need multi-constellation and full-band antennas to benefit from Galileo's new high-accuracy service, in addition to all the other GNSS signals, traditional single, dual, or even triple-band antennas just won't cut it. With the addition of HAS, the requirement for high-performing, higher bandwidth antennas has become more mainstream. The challenge now is to build an accessible antenna in both size and in cost that supports it all. And there is no free lunch, and the idea is to design the antenna while maintaining performance and meeting all the requirements, which brings us to the next aspect of a good antenna. What makes a good antenna? The antenna is the first component in the positioning system to receive and process satellite signals. A bad antenna ultimately results in poor GNSS performance. Think of the antenna as the lens of a camera. A sharp lens is imperative to achieve high image reproduction fidelity. Like how the image on the right shows the osprey catching a fish. Look how tack sharp it is. Likewise, a good antenna is imperative to achieve precision down to the level of the phase center variation, in essence, the antenna's physical limit. If you have a Ferrari, you don't put bicycle wheels on. Even though there is so much that can be done in digital signal processing at the receiver level, having a bad antenna that does not reject interference and saturates the receiver, for instance, there is no coming back from that. So choosing a good antenna is critical. What makes a good antenna? To explain this, let us go through the life cycle of the GNSS signal as it is captured by a good antenna and travels down the RF pathway. The right-hand circular polarized, or RHCP, GNSS signal first encounters the antenna element. To capture the signal, the antenna must be circular as well, and we're going to get to that on the next slide. Not only does it have to be a circular antenna, it has to have gain, high enough gain to amplify the weak GNSS signals. The plot to the right shows the radiation pattern of one of Talisman's high-performing antennas. The black curve describes the gain of the antenna in over every angle in space. As we discussed in the previous slide, to capture a circular signal, you need a circular antenna. This is not entirely true. A linear antenna can capture a circular signal, but only half of its power. To get the full power, you need to match the circularity in the antenna. This circularity is measured as axial ratio. A low axial ratio means a high reception of right-hand circular polarization and a low reception of its opposite, left-hand circular polarization. A good antenna has low axial ratio to capture the direct GNSS signal and to minimize capture of unwanted multipath or reflected GNSS signals, which are left-handed. A third point is where the signal is received. Every good antenna has what you can call the point of coalescence or a phase center. However, every antenna's phase center varies. Take, for instance, an incandescent light bulb from the days of yore. The light source appears as a point where the filament is located. However, you will notice that as you turn the light bulb around, that point appears to move and its position varies. This is because of the way the light is refracted by the glass. The unevenness in the thickness of the glass creates this variation. Similarly, in every antenna, there is phase center variation. A good antenna is a well-built antenna based on a technology where the phase center variation is small. The smaller the PCV, phase center variation, the more precise we can be. Moving on to the next stage of the life cycle, entering into the LNA. Once the signal passes through the element, it has to then be processed. Of course, it may not only be the GNSS signal entering, but also interference signals as well. These are unwanted and must be mitigated. To do this, we could use pre-filters and extended filtering, or XF technology. With GNSS signals being weak, the sources of powerful terrestrial-based interference like cellular, LiDAR, USB 3 can become problematic. Luckily, there are ways to help prevent these interferences from affecting the GNSS measurements. By using a pre-filtered antenna or an antenna with extended filtering technology. In the graph to the right, you see the response of a pre-filtered antenna in black and an XF antenna in red, showing more than 80 dBs of out-of-band rejection. This helps suppress unwanted signals to provide a clean and pure GNSS signal at the antenna output. So we have learned a good antenna rejects out-of-band signals. Once the signal reaches the output of the antenna, the signal strength is determined by the G/T overall. A good antenna must have a high G/T, or gain to noise temperature ratio. Of course, we have spoken about the gain aspect of it, but the other side of the fraction is noise figure. And to maximize G/T, the antenna needs a low noise figure. At the end of the day, the antenna is connected to a receiver where signal to noise ratio values, or SNR, is what matters. This example shown here shows a variety of satellites at different points in the sky. To the left, you see the SNR values for the signals being received from these satellites. These numbers are fairly high, but wait, the keen of you among you will notice that a pre-filtered antenna or an XF antenna with additional filters would tend to raise the noise figure of the antenna because of the insertion loss. That is true, and of course there is no free lunch. Having additional filtering will slightly impact SNRs. However, that is the trade-off we make to allow the good antenna to be resilient when operating in the presence of interference. Where a non-pre-filtered antenna would fail, a filtered antenna would thrive. A good antenna does not only have good filtering, but is also optimized to minimize noise figure. All of these characteristics are in the context of a good full band antenna to cover Galileo's HAS. A good antenna should have high passive gain, low axial ratio, small PCV, and it should reject interference, have a low noise figure, and here's the catch, all within a small, light, compact, and affordable package. Are we not reinventing the wheel here? Surely there are other antennas that have all of this and are suitable for Galileo's HAS. And it is true. These full band antennas do exist, and Talisman offers many survey and geodetic gradient options as shown here, such as the Verichoke, the Veriphase, and the Veristar lines. However, these may or may not be suitable for certain applications where swap-C factors must be considered. Novel full band solutions are being introduced where they're designed with size, weight, power consumption, and cost constraints as paramount. With pleasure, allow me to introduce these two novel solutions. The first solution stems from the latest evolution of the Veristar product line. At first, the Veristar was developed and it was then miniaturized into the Veristar Mini. Now it was further miniaturized and repackaged as the SSL 990XF, or as we like to call it, the Micro. Firstly, this antenna is full band and it has excellent coverage of HAS. Its element allows for excellent multipath rejection. It has a small PCV, it comes with XF technology, and it is super light and super small. This antenna performs optimally with a ground plane. The next solution is an advancement on the traditional helical technology to bring a true full band coverage to this lightweight product line. The HC990XF is optimized to cover HAS well. Like the SSL 990XF, it also has great multipath projection, small PCV, and XF technology. It is super light and it is super small. But for this solution, the antenna performs well without a ground plane. Let's recap. With the emergence of HAS, the industry is trending toward demanding good antennas with full GNSS band coverage. we enumerated key GNSS antenna performance characteristics that would help in selecting a suitable antenna to use with Galileo's HAS. To provide accessible options that enable the use of HAS in a wide variety of applications, two novel full-band solutions were reviewed, the SSL 990XF and the HC 990XF. In addition, Talisman offers a wide range of full-band options and also other options that focus on the Galileo E6 coverage on its own, such as with ceramic patches. Ultimately, with the precision benefit of HAS, with the precision benefit that HAS can help bring worldwide, Talisman is proud to provide advanced solutions to help anyone take advantage of this new service. With gratitude, I pass on the torch to Jean-Yves as we continue our presentation.
Thank you, Joe, and good day, everyone. The part of the presentation here will be mainly on the results that we get using the Galileo HAS the way it is today and how it started earlier this year when it was released for phase 1. A couple of the slides will be some repeat of what Sunil said, but removing the type of brain cell that he has and keeping the average normal people cell that end users in the field have. So with this, I will go back again, recap a little bit of the basic principle of HAS. It's important to understand that the corrections are broadcast by 20 of the orbiting satellites, 20 of all the orbiting satellites of Galileo. So they orbit around the Earth, compared to conventional EUSPAs that we know that are geostationary. So the principle is that monitoring stations around the Earth gather information, sent to a data center that generates corrections, and that are being sent back to uplink stations, and that rebroadcast the corrections to the satellites, and in turn those satellites broadcast the corrections to us users on the E6 band, E6 frequency that Sunil and Joe have mentioned before. So that's how it works. These are the basic principles. So, and the satellites participate, each of them, in a little bit of the messages. So we always have messages, if you want, around to receive from those orbiting satellites. And again, to recap here, just a difference, to emphasize the difference that we are currently in phase 1. There was phase 0, there was feasibility, and phase 1 is basically beta testing, if you want. And that there are, repeating that graphic from EUSPA that Sunil showed earlier, we are currently service level for everyone without the phase biases, as he mentioned. So conversions is a bit longer, and they are working right now towards phase 2, and that implies a lot of things. We're working on all their algorithm. I mean, their infrastructure, if you want to install more stations and polishing a lot of things. So it's a tremendous amount of work. But again, I would say a very innovative system from European space, from EUSPA. So currently we're in phase 1, and there's no clear date yet when we're going to go into phase 2. Phase 1 was announced officially earlier this year in January. And again, Galileo, just to make sure everybody understands, Galileo broadcast corrections for GPS. The Galileo HAS broadcast corrections for GPS and Galileo. I should say Galileo and GPS, but not the other constellations also. And we were surprised also to see that they included the L2. Initially it was supposed to be L1, L5, E1, E5, but then L2 was added for GPS, which makes a difference also. With this, we decided, when it was announced, we decided to do some testing. And what we used was the Arrow Gold Plus receiver, which was launched about 2 years ago by EOS. And then that was in anticipation of the Galileo HAS coming up. And of course, we were looking for an antenna and reached out to our dear friends at Talisman, and they had the V6037. I said, well, it's too big. And in no time, I was surprised that they got a phone call, hey, got something for you. And the 6028 was born out of the 6030 with a smaller form factor. And this antenna has had tremendously good results, mainly with the low elevations signals, and very innovative and very lightweight also. So that's why we decided to built our own enclosure, and it's called the full band antenna that we use with the Gold Plus, which is a full band receiver that tracks every single possible signals and satellites from all the constellations. And with the antenna set off on the roof here in Montreal, Terrebonne, suburb of Montreal, we started getting, this was the very, very first test that I personally did. It's about a 17-hour log. And we can see that the accuracy, I'm sorry, before I go there, the concentric circles are 10 centimeters apart. So immediately we went down to about 40 centimeters, almost instantaneously in a matter of seconds. And then the receiver stayed there, I mean, the location, if you want, orbited there for a while. And then with time, it got better, as Sonia mentioned earlier. With time, that's the nature of PPP. The more observation you get, the better it gets with time. And we're able to finally go into that sub-foot after, I would say, about 15, 20 minutes, and then down to the 20 centimeter that EUSPA broadcasts, advertises for that. But then what was surprising, the following day I came back and I saw all those points, the cluster of points was within an average of about 5-7 centimeters away from true location. So results are very good, but the problem is the time, how long it takes to converge. So convergence time is the key issue. And again, as was mentioned before, it has to do with a whole bunch of other factors that I will cover later also, but mainly that not all the information is being broadcast for Galileo HAS during the phase 1. And once phase 2 is announced, the infrastructure will be ready, then we'll go down basically in less than 5 minutes, we'll go down within 20 centimeters to DRMS. 95% confidence will be within 20 centimeters horizontal, and 40 centimeters, 95% confidence within that same time period. And for Europe with service level 2, Europe will enjoy below 2 minutes convergence times. And we also gathered information, and with help of some friends in the industry, and comparative logs between Europe and Canada and North America, let's say. So you can clearly see from that graphic that convergence time, even without the phase biases being broadcast in Europe, are much faster, in this case, Italy. And you can see that the average orange line, you can see that after about, I would say, 5 minutes, you're down to about 20 centimeters in average, and it gets better with time. Whereas in North America, it takes a bit longer. We're talking about 15 minutes average to get down to the 20 centimeters, the specified 20 centimeters. And you can see that it's noisier elsewhere outside of Europe. And with this, also EUSPA in the past had this diagram on their site saying that they don't guarantee the service in the shaded area of the Earth. Why is that? Means that doesn't mean it doesn't work. For example, in Australia, those eastern regions, if you want, it's just that they cannot guarantee that they're going to get those type of 20 centimeter accuracy in a reasonable time. But it still works, and they're testing that our customers perform also in Australia and this region and Southeast Asia, and the system does work over there. And it's gotten better since then. And the reason for all this, you look at the spread of the current monitoring stations that they have in the world. Of course, Europe has a lot of monitoring stations, and there's more data available, and that's why the conversions today in Europe are better than the rest of the world. Since then, they have added a couple of stations next to southeast of the Caribbeans, and I think in the Pacific also. So their mandate right now is to increase the density of those monitoring stations so that they can achieve that phase 2 with the proper convergence time. And I will finish the presentation with a couple of thoughts. And EOS by default is in high accuracy for mapping applications. And we can look at the strength of what Galileo will bring, such an innovative system. Of course, a worldwide accuracy of 20 centimeters to the RMS. And what Galileo HAS does, it fills a missing gap, I would say, between the sub-meter that we're familiar with conventional SBAS that are made for aviation, like WAS, EGNOS, MSAS, GAGAN, and now Southband in Australia. It fills that gap from the sub-meter down to the centimeter level that we're familiar with doing RTK. And the other innovative aspect is that the 20 orbiting satellites participate in the transmission of signals. So when the south, for example, in the northern hemisphere, the south is blocked and your geostationary satellites you cannot receive from them, whether it's WAS or private PPP, paid PPP, it's blocked, then you still have the orbiting satellites of Galileo that you can receive the information from. And at extreme latitudes, it makes a huge difference also. And you don't require internet connection, even though the Galileo has broadcast what they call the IDT, Internet Data Distribution. For the majority of our users, this is not going to be profitable because most of the people that are there for mapping and field data collection, if they have access to RTK, that will be the preferred choice if they need high accuracy. And if they don't have internet connection, then HAS can come to the rescue with an average of about, I would say, RMS values of about 10, 15 centimeters, which is better than nothing. And of course, the system is free. And I want to also mention what will HAS do and what will not, and what is HAS not intended to do. It is not intended to replace RTK for very accurate as built, for example, for constructions. But if we compare HAS, we look at all the benefits, but compared to what we call traditional SBAS, because HAS private satellites, again, they're all SBAS, but what we know as the one made for aviation that we use for mapping that provide code differential for sub-meter was EGNOS MSAS. Again, it's an increase of accuracy. Even though our receivers is able to do 60 centimeter accuracy horizontal, 30 to 60 horizontal with WAS, for example, or EGNOS, with HAS, we go one step higher in what we obtain with the 15 centimeter. And if we look at the paid PPP satellite services, those, yes, they are paid. They are geostationary paid services, and they provide a little bit more. They provide a faster conversion. Sometimes they provide better accuracy also, and they provide corrections for all constellations usually. So they don't replace paid PPP services that have their purpose, but they can add also when those are blocked, for example, by buildings and they are obstructed. So HAS also can come to the rescue. And again, for RTK, it will not replace those centimeter accuracy that we get XYZ with RTK, but again, it will be there as a backup also sometimes. And if we compare HAS with regular traditional SBAS, there's another way, something that is very important to understand is that PPP uses carrier phase. So carrier phase cannot be used normally under obstructed conditions, under foliage, for example. This is very different from code differential. This is why SBAS in our receivers, SBAS can perform very well and provide all the GPS accuracy, if you want differential GPS, GNSS accuracy throughout the day. Whereas PPP, and once you require a carrier phase, you require a certain observation time in order to converge and fix your ambiguities, which RTK does almost instantaneously because it's local, and PPP uses different techniques, so it takes longer because there's no nearby base stations if you want. And having said that, also don't forget that SBAS, conventional SBAS, was EGNOS MSAS. They broadcast corrections only for GPS. Yes, we can include their techniques that we use in our products to include all the other satellites in view, but primarily they are sent for GPS, with the exception of Southband in Australia, which is becoming innovative, and they call what they have the DFMC, dual frequency multi constellations, and they are broadcasting corrections for Galileo and GPS E1, E5, L1, L5 also in their service, and providing also PPP corrections now, which is also very innovative from South Bend, Australia. And basically, the market segments that will benefit from Galileo HAS is a repeat of what I said earlier. It's everybody that would fill that gap between sub-meter and centimeter accuracy. And when you're in the desert, in the middle of nowhere, no internet connection, you do have a source of about decimeter to half a foot accuracy that is available to you. So with this, I'll pass it on to Jesse for Q&A. Thank you.
Thank you. So right now we're going to jump into some pre-registration questions, as well as some from the live event. So first, Sunil, can you please clearly differentiate between HAS and normal Galileo? Is HAS a correction signal like EGNOS, WAS, or commercial correction and augmented services? If yes, please clearly differentiate between them.
Thanks, Jesse. There's a few questions there, so I'll answer it this way: that so Galileo that most people know and use is the open service. Galileo HAS, HAS, is a correction to that correction. So the open service broadcasts orbits and clocks and other information at a particular level, and HAS that's being transmitted on E6B is an additional correction that's applied on top of the Galileo correction, and then on top of the GPS broadcast orbit and clock information. So it's different. Now, when we talk about EGNOS, or in North America, WAS, these are other EUSPA, space-based augmentation systems that are designed for primarily aviation use, but they're as much for integrity and availability of solutions as they are about precision, and they're also focused on pseudorange or code-based measurements. So they are different. Hopefully that's a clear enough explanation. Jesse?
Thank you. Now we'll go on to Jean-Yves. Can any Galileo capable receivers also take advantage of HAS? If not, what is the incentive for manufacturers to add HAS support to their hardware?
Well, depends on well, first of all, to answer the first part of the question, not all of them. I mean, you might be tracking Galileo for positioning, like the E1, E5 signals, and they are used for positioning. But in order to be able to use Galileo HAS, you need, first of all, the antenna capable of receiving that signal on the E6 band. And also, you're supposed to, what you need also on a receiver is the capability to process those PPP signals, because not all receivers are capable of doing that. This is a very specific part, if you want, of the GNSS receiver. And the second part, and the second question, I'm sorry, say that again, Jesse.
You're fine. So the second part of the question was, so if not, what is the incentive for manufacturers to add HAS support to their hardware?
Depends on where their target market is. If you are, it depends really. If it's purely very difficult question to answer. On the mapping side, yes, definitely it's going to be useful because people work all over the world, on water, on land, for example, in Africa, Latin America, where there's no free differential correction service from the conventional EUSPA system. So that could be a big game changer where they get accuracy in the middle of nowhere, sometimes with no infrastructure. And this is what is important. If you're really working within cities that have, for example, free RTK coverage, for example, in North America, you take a lot of them operated by Department of Transportation, like Florida DOT or New York DOT, they have free RTK network and basically cell phone coverage throughout the entire state. And yes, you could make use of that, and probably it's not beneficial to implement all this, because then priority will go to those local correction systems. But again, in those marginal conditions where cell phone is spotty, because which is the case in every single place in the world, there are places where cell phone is spotty, and HAS comes to the rescue.
All right,
Hope that
thank
answers your
you.
question.
Next, we'll move on to Joseph. So resilience to interface is a hot topic these days. How do your antennas at Talisman mitigate this interference?
Thanks, Jesse. So, well, we did talk about during the presentation that we can use a pre-filter to mitigate interference, but pre-filter alone is generally wideband, and it can generally let in things at the really low frequencies and the really high frequencies, or sorry, it blocks out signals at the really low and the really high frequencies. An example would be cellular networks around the 600 to 700 megahertz range. With the XF filtering, the pre-filter that's being used is actually dual band. So it blocks out everything below the lower band, above the upper band, and in between the lower and the upper band. And it gives about 40 dBs of rejection at the get-go, just before the first gain stage. When it comes to the XF, there's also other filtering stages in addition to that. So you get pretty deep rejection there, and that helps mitigate interference. There's also, we do have an anti-jamming line of antennas does exist. And in an anti-jamming line, there are actually 3 levels of protection. So XF filtering and pre-filter, that's the second line of defense. But the first line of defense would be spatially. So beamforming and creating a radiation pattern where there's potentially less gain of the antenna in places where you don't want gain, say near ground level, where there's a high risk of having a source of interference present or an intentional jammer. In addition to that, there's fixed beam, and then there's adaptive beams, so controlled radiation pattern antennas that can be used to do this. That's spatial. And the filtering is the spectral, so there's spatial protection, spectral protection. And then at the very output of the antenna in the LNA, there's the last gain stage. There's the possibility of using something to protect against saturation. So a more robust, rugged output stage to provide a higher output P1 dB or a higher linearity. And altogether, these are some of the techniques that we use to mitigate interference.
Thanks, Joseph. So the next question is for any of you guys who want to answer. This was one of the questions from the live presentation. It says, practically speaking, how can I use the Galileo HAS service? Do I need credentials such as like an RTK or paid PPP? And how can users access this?
I think that would be for Sunil.
So the signal is live. It's being transmitted by the Galileo satellites. There also is a web-based version. But if we're referring to the signal in space, what's required is a receiver that that has an antenna that can receive the E6B signal that then can decode the E6B signal, and then the user would have to have the software to process those additional corrections. That is a PPP software. So the signal is available, but you would need the receiving equipment to make use of it. But as we said, the ICD has been available for a while, and companies on this webinar and others have built decoders and firmware into their receivers. Jesse?
Thank you. Another question that came in is 300 seconds as declared HAS coverage time seems to be too optimistic. What is your opinion?
Do you want to start on that one? Because I think it's a two-parter. You can go ahead.
Yeah, I think it's. I don't think it's optimistic. I mean, if some private PPP today are achieving conversions times sometimes below that. But I think that the more stations that EUSPA, European Union, will put to cover, to densify, if you want, the network, specifically for Galileo HAS, because right now they're using the monitoring stations for Galileo, and they want to have the stations for specifically Galileo HAS. So once they densify that, we will see the convergence times go down. Right now, we see them in Europe. Again, they are within 5 minutes today, and they're not even podcasting the phase biases right now. Imagine when they do, that will speed up the conversions already in Europe. I think it's just to launch the full phase biases, and you'll see conversions times met per specifications in Europe. So I think it's not too optimistic. It's doable. Sunil.
I absolutely agree, and we've showed some results with geodetic stationary geodetic equipment where the 300 seconds is being met. 5 minutes is, remember, and the specs are less than 5 minutes in the world with service level 1, and less than 100 seconds with service level 2 in the European area. As Jean-Yves said, once we have the phase biases, that those convergence periods will speed up. There is a question in the chat about when will the phase biases be transmitted or be available, and so that was a question that I asked our colleagues at EUSPA just a couple of weeks ago, and they in public have said they're coming. There was another question in the chat talking about the ground stations and expansion of the network, and they are also, EUSPA is also working on. They have this year added a few ground stations, and they're working quite hard to add some more. So Jesse, that answers a few questions there. I'll pass it back to you.
Perfect. Yeah. So there's another chat question. It says, is HAS availability a threat to RTK, or does it go hand in hand when it comes to areas with good internet connectivity and autonomous or automotive applications?
I think I covered that. Probably the question came after I covered this topic. It's not going to replace the accuracy of RTK, but I think it can supplement, if you want, in cases where you don't have good RTK signal, but you still have something when you're in the field to do some accurate mapping.
Yeah, and I can just add to what Jean-Yves said, and that is that what we're seeing, especially, for example, the specifications for HAS and other similar space-based navigation system sort of PPP type corrections, is that it's filling a gap between the meter level, as Jean-Yves said, and the few, let's say the 2 centimeter the RTK, and the same with some of the commercial PPP services as well. I don't think there's an interest by governments or to compete necessarily with the commercial, the private sector. So these solutions are in between, and we'll, as we've seen since the beginning of GPS, new applications are born from the new technology. So it'll be really exciting to see what comes of these corrections that are available.
Yeah. And I'll just add one last thing, is just that even the private PPP, they can achieve accuracies of about 4 or 5 centimeters today. So it's a little bit more than closer to RTK, and a little bit more than what Galileo has to offer.
Perfect. And we have time for one last question. This one is for Joseph. How do you design a small compact antenna, and then what are the pros and cons?
Thank you, Jesse. Well, with regards to a full band antenna, size volume helps. A bigger antenna is helpful to get the best performance in the whole bandwidth. But when it comes to miniaturizing it and still having a full band antenna and having great performance, you start running into a bunch of problems with perhaps manufacturing tolerances and more mechanical issues. And you run into the limits of physics, of course. So a lot of techniques we use are like maybe common and not so common miniaturization techniques, which help us get, for example, the Veristar line and helical antennas to be a lot more compact while keeping the performance really high, really good, low elevation, so mitigating a lot of the problems with interference and multipath, and still being full band, having good performance. So yeah, really it's all about just precise tuning and using the novel miniaturization techniques to bring the size down. Thank you, Justin.
Thank you all for the great presentation today. Now we're going to wrap up the live event. Thank you all for attending the Galileo High Accuracy Service Features, Hardware, and Applications webinar brought to you by GPS World Magazine and our sponsor of the event, Talisman. If we were not able to answer your questions during the presentation or Q&A session, your questions will be forwarded to the speaker to be addressed via email. A recording of this webinar and other upcoming webinars from GPS World will be posted to gpsworld.com/webinars. Thank you all for attending, and we hope you'll join us again soon for another great webinar.